Hey there, Calc folks, back here with another lecture in our series of lectures where we're here looking at application of integration. And here we're going to take a look at area between two curves, looking at the process of integration and calculating area between two curves. And by that area, I do mean physical area versus net area. There is that difference, right? Net area takes into account for direction that this area forms, either direction above or below the x-axis. What we're looking at is just physical area space. You know, how much carpet would you have to buy to carpet this region of space, right? That physical geometrical measurement of area, right? Where this idea of area between two curves prepares itself from, right, folks, is it does come from the idea of that net area concept, right? To find the physical area between two curves, we are going to rely on that net area concept that we presented back in Calc 1, right? That is kind of the underlying interpretation of the integration process, right? Or the value of a definite integral, right? And we understand from Calc 1 the net area trapped between some function in the x-axis over values of x in this closed interval from a to b is calculated using what we call the definite integral calculation. That is this calculation right here, right? And if we understand regarding this calculation that when this calculation is performed, when we evaluate the definite integral, we do get a numerical value for that value, right? It does not produce the antiderivative function, although the antiderivative function is used in that calculation process. We just take it a step further and evaluate that function over these bounds from a to b, right? But what we also further understand from this is that it illustrates a net area calculation. And if we look at an illustration of that, I give a quick little illustration of this down below here. If I made this a little bigger, you could see that illustration. Here we have the integral for our function f of x. F of x is this curve, and we're calculating the net area of f of x, the definite integral calculation, over values of x starting here at a and continuing down here to b, right? That net area trapped between the curve is all the area seen in this bluish region here, all this area seen here in this reddish region here, and then again all this bluish area seen here in this region here, all right? All of that area is considering the net area in this calculation. This calculation is interpreting the net area seen in all three of these shaded regions, right? Where we understand from net area, the concept of net area involves not only indicating physical amount of space, but also being an indicator of direction in which that space forms. Here we have some space forming in the positive direction above the x-axis, and here we have some of this region forming, this net area forming below the x-axis. When calculated individually, the regions forming above the x-axis, this small little region here or this larger region here, would both give positive net area calculations over their bounded regions alone. Whereas if we were to calculate the net area of just this little region down here underneath the x-axis, shaded in red, it would be a negative value in its net area calculation. All right? And altogether, if we were to then consider the calculation from a to b for f of x dx, what it would be giving us is the measurement for all this positive area minus the measurement for all this negative area, right? It would be this area, and with this little region taken away from it, right, in its calculation. All right? That is net area, folks. All right? And that is the illustration of net area in general. Now this net area calculation, right? We can go on to use that to actually consider calculating and understanding a physical amount of space trapped between two curves. And this calculation is defined as follows. All right? By definition, the area trapped between the continuous curves f of x and g of x, where the output values of f of x, the values trapped are tracked along the vertical axis of space, are always bigger than or equal to the output values of g of x on that y-axis or vertical axis of space over values of x in this closed interval from a to b is given by this integral calculation seen here. It is an integral from a to b, a definite integral from a to b that happens with respect to our independent variable x in this functional relationship, where the integrand is composed of taking function f of x and subtracting from it function g of x. All right? We are looking at the difference between these two functions. And if you keep in mind, what is difference? Difference is distance. We are integrating over the distance between these two functions from a to b. Right? We are figuring out how far apart vertically are functions f and g at every single value of x from a to b. And this can be seen in the following visual illustration. Here's the illustration of this case. Here's the graph of f of x, right? And that is occurring over this region from a to b. Here's the graph of g of x, right? This parabola opening upward. It is occurring over this region from a to b. And what we can calculate here for this region is the physical area trapped in this shaded region of space between these two curves. And what we are integrating here, folks, from a to b, we are integrating function f of x, the area trapped under f of x, which would be all the area between f of x and the x-axis, minus the area trapped between g of x and the x-axis. That would be all this area trapped between g of x and the x-axis. We're going to take the area between f of x and the x-axis and subtract from it this area underneath g of x, trapped between g of x and the x-axis. And what that leaves behind is this physical area seen here in the shaded region. Now again, what we are doing, folks, is from a to b, in the integration, well, let's back up a second, just so we can start to understand what is integration showing us. What are these ideas, some of this idea behind integration. And this is going to come out a little bit later as we get a little further into the chapter, and I want to go back and formalize some of these definitions with some proof. All right, with a quick video and some proof. Looking at the actual essence of integration, what is integration actually doing here, folks, when we calculate this? All right, when we apply this operator to some argument, all right, what that operator is doing, if you keep in mind in terms of the background or how it's defined, it is a limit for a summation, right? It is a limit at infinity for a summation, right? It is what we call a limit of a Riemann summation, where here this summation is going to add up all the differences between f of x and g of x. At every single value of x is the values here trapped along this horizontal axis, at every single value of x, there is a difference between the value of f at that x and the value of g at that value of x. Right? That difference between f and g occurs at every single value of x along this x-axis. Between a and b, it occurs here, it occurs here, it occurs here, it occurs over here, and it occurs at an infinite number of locations between a and b. Right? That difference or distance, right? This distance seen here, right, occurs at every single infinite value of x, and what we can do is we can add it up for every one of those infinite values. And you go, well, how do we add up something that goes on to off to infinity? Is we actually examine its behavior using that limit as the number of subdivisions of that interval from a to b head to infinity. That is that limit of the Riemann summation happening there. And it gives us this physical area trapped between these two curves in this case of integration. All right? If we go a little further with this, right, look at an example, we might consider finding the area trapped between the curves y equals x squared and y equals 2 minus x over values of x in the interval from 0 to 1. All right? Here is our equation y equals 2 minus x. It could be thought of as being a function of x. 2 minus x is some linear function of x. And here is our equation y equals x squared. It is itself a function of x, right? X squared is the square function of x. And we are interested in the area of space, the physical area of space, trapped between these two curves over values of x along this x-axis, starting at 0 and continuing on down here to the value at 1. It's this region of space we have shaded in this illustration. There's a physical amount of space there, right? And we can find it if we go to every single value of x between 0 and 1, and we look at the value of the function seen here, right, at the top, or at this function y equals 2 minus x, and we subtract from it the value seen here along this curve at y equals x squared, we're going to get the measurement for this linear length between this upper bound on this region, or that length, and this lower bound on this region and that length. That difference, right, accounts for that little bit of tiny bit of space, right, seen at that value of x, that infinitesimally small or thin line of space. And that infinitesimally small or thin line of space occurs at every single value of x from 0 to 1 and has a different length depending upon the upper bound on that length given by 2 minus x and the lower bound on that length given by x squared. And what do we have to do to figure out the total area is add up all those infinitely small lengths of vertical space. And we do that across this entire region from 0 to 1, and that occurs using that definite integral process, right? That occurs using definite integration, right? This integral from 0 to 1, that is what integration represents in the background. That is the essence of integration. It is an infinitely long summation. And the way we approach that infinitely long summation is with the use of a limit. Right? In this case, the area would be calculated as the summation that would occur from 0 to 1, so that is a definite integral across this region from 0 to 1, where we want to look at the difference between f of x and g of x. F of x is going to mark the top of these lengths, and the top of these lengths is all described by 2 minus x. So that is the first function in this difference, right? Whereas the bottom of all these lengths is described by the square function. So that is this x squared, the second function in this difference. This is our f of x. This is our g of x, and we are taking f of x minus g of x in our calculation here. When we do that, composed inside this brackets, and simplify that, we just have a quadratic polynomial. If we take a linear function and we subtract from it a square function, that forms a polynomial function. So really what we have here is the integral from 0 to 1 for the polynomial function 2 minus x squared, or the quadratic function 2 minus x squared. Where through our fundamental rules of integration, right, we can distribute the operator across these differences. We can pull out any constant multiples, and we can follow we can apply some power rules for x to the 0, x to the first, and x squared in power. If we do that, the antiderivative is what? 2 times x minus 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1. Right? That is the antiderivative of this integrand. Right? Where we're going to now evaluate that from 0 to 1. So at 1, we substitute 1 into all these locations. And that will give us what? 2 minus 1/2 minus 1/3. Right? Which, if I remember correctly, is 11/6 in value. Or sorry, 7/6 in value. Right? That's 12/6 minus 5/6 would leave us 7/6 in value, right? Minus, when we substitute in 0, well, you just get 0 out of that. So 2 minus 1/2 minus 1/3 minus 0 is 7/6. And 7/6 units squared describes this physical region of space. How big is that region in terms of area? Well, that is 7/6 units squared in physical area. Right? And we were just using there that definite integral operation. We were summing up in this integral seen down below here all the infinite differences between these graphs. What are all the infinite differences between these two graphs? That is the distance between those two graphs. So if I know the distance here, and I know the distance next to it, and I know the distance next to it, and I know that distance next to it, and I know that distance next to that, infinitely long across this region from 0 to 1 for x, and I add all those infinite lengths up, that is what comprises the concept of area. And that's what makes up this area calculation. Now, in this calculation, we were looking at those lengths forming vertically between this function that occurs in the upper region, right? In this case, it's that function, it's that function, I'm backwards here in the video. That's that function y equals 2 minus x coming through space here. That defines the upper bound of this region, right? Whereas the lower bound of that region is defined by that parabolic curve sweeping through the space here. And we are looking at the lengths vertically between these two graphs. That is one orientation we can approach this with. And when we approach it in this context, looking at the area trapped between these curves as this sum of lengths that form vertically between these curves, that is what we would say is the vertical orientation for this calculation. And it is approached with this first definition. However, well, I should say this is kind of more the classical approach, classical to our understanding of algebra. What we don't do in algebra too often is switch dependency of our variables, right? We often approach a two-dimensional system back in algebra with x is always the independent and y is always dependent upon the value of x, and with the context of y equal to f of x, right? Presenting ourselves with this dependent-independent relationship where y depends upon x. We very seldom swapped our dependencies. We very seldom considered the cases where y might be independent and x is dependent upon the value of y. We very seldom considered graphing our functional curves with a vertical illustration, with a flow vertically through space as opposed to this horizontal flow through space that we see in the classical case, right? And if we were to consider swapping our dependencies, this calculation for area between the two curves could also be considered in a slightly different context. And that is the second context we see here, right? Distinguished in this set of notes. Note, the above setup for area trapped between two curves considered the case of the area trapped between two curves orientated in R2 where y was dependent upon the value of x. X was treated as that independent variable in the description of these curves, right? A similar setup can be seen for the area trapped between two curves in two-dimensional space, where the curves are defined within the context of y being that independent variable value and x being dependent upon y. All right? In this case, if we were to have a scenario with, x as our horizontal dimension, y is our vertical dimension of two-dimensional space, and we were to consider a relationship between x and y where y was an independent variable in a functional relationship with x depending upon y, our graph would flow vertically through that space and would all pass a horizontal line test, as opposed to what we saw back in the more classical interpretation. All right? Now, most graphs in space can be approached with either variable within that, context of being dependent or independent. What it takes from you is going about and redefining that relationship to define that particular dependency in the relationship. We're really used to that dependency being already defined for us in the case where y depends upon x. When we've approached this scenario given above, y equals x squared and y equals 2 minus x, where relationships between y and x, where the dependency was already illustrated as y dependent upon x. We're going to see that not always is that the case, and sometimes we're going to get to choose our dependency, depending upon the orientation that we want to use as we set up this area calculation. And pending that orientation, we can sometimes set up a more complex calculation, or we could even make our lives a lot simpler and set up a really simple calculation, just depending upon the graphical nature of the illustration, right, for that area between two curves. Note, right, if we go down and look at the definition for what I'm referring to, it doesn't look too much different from the definition we've seen above for the classical orientation. However, here, what we do take note on is that we are looking at functions here where x is equal to f of y or x is equal to g of y. Right? Highlighting in this relationship that x depends upon y. Y is the value seen in the parentheses in these functional descriptions, meaning that y is the independent variable value. Right? A line flowing through space could be thought of as being both in an independent-dependent relationship where x might depend upon y or y might depend upon x. In this case, we would approach that line with the understanding that x would be dependent upon y. And when defining our functions f and g at y, right, we would consider taking that linear equation and making sure that it was solved for x on one side of its equation. Now, furthermore in this relationship, we do have to take note of size of outputs, f of y, will have to be greater than or equal to, let me fix this, g of y, right, over values of y in this interval from c to d. All right. Y, c to d is some vertical interval of space, not horizontal, because it is referencing y values as opposed to x values. All right. And in the case where y is this interval from c to d and our functions form vertically through that space passing the horizontal line test, what it means to be larger as an output in that space means to fall further to the, with my video to you here, that means to fall further to the right of the screen here in space. If a graph flows further to the right of the screen, right, than when compared to some graph that might fall to the left of it, its outputs would be further away. All right. Let's look at a specific case here, folks, of all this. Consider the area trapped between the curves y minus x equals 0 and x plus 2y equals 8 and y equals 1. Consider the area trapped between all of these curves. All right? I do help you out in interpreting what that area would look like. And it would be this region seen right here, this triangular region seen in this space, where our lines defining this region of space, right, or these equations defining this region of space, aren't truly curves. They're more linear in their behavior. But notice, are not defined with any context of dependency. Y minus x equal to 0 does not illustrate one variable as dependent upon the other. And neither does x equal to 2y, or x plus 2y equal to 8. It does not illustrate any dependency on one variable or the other. Y equal to 1, well, that is just a one variable linear equation that defines that horizontal line in space. All right? Certainly that would be a constant function, right? That is illustrating a constant function where y depends upon x in that equation. Another way we could even think of that function, if we wanted to illustrate it with no dependency, is we could say that is y minus 1 must equal 0. That's another way to describe that line in that space. But let's leave it as the more familiar y equals 1. That one equation is defining a little, you might see that as a functional relationship where y is dependent upon x, because what we have here is a, what? Constant function of x. All right? Constant function of 1. Well, in this case, we can either consider this region of space forming in the vertical orientation, the more classical orientation, where we would be interested in calculating its area by finding all the infinite vertical distances between the top of this region and between the bottom of this region. That would be our more classical orientation. That would consider treating y as the dependent value and making y dependent upon the value of x, x being independent, meaning that in these equations I could solve them for y, so y equals x would be 1. That actually would describe this path. And I could describe over here, it would be, what would that be? Y equals 4 minus 1/2 x. That would be this path. All right? And the top of those regions would be described by those two functions, y equals x and y equals 4 minus 1/2 x. Right? And that would be a more classical approach to defining this region, and that would be perfectly fine. But what you might notice is in that approach, you're going to have to approach it piecewise. The upper bound on those lengths, when we go from the bottom of those lengths up to the top to figure out how long this region is vertically, the top changes its behavior. It changes from the line y equals x to the line y equals 4 minus 1/2 x, right? Described by this functional relationship seen here in the context of x being independent, right? It changes right at this location here, where to approach this in an integration, you would actually have to approach it piecewise using two separate definite integral calculations that are added together in the end. Let's look at that. I do think I give that summary here in the notes. Note, in the context of x as the independent value in this description of space, the area could be calculated piecewise as follows. Now, I went ahead and did the algebra here. You would have to do some algebra to figure out this location. Set this relationship equal to this relationship, and that is where you will find this intersection point. Now, you would have to solve them for their y's and then set those two values of y equal to each other and solve for x. And that's how I know this location for x is at 8/3. Right? Just a little bit of algebra will tell me that by finding this coordinate on both lines simultaneously. Right? And my first integration, this first region forms from 1 down to that location at 8/3 along the x-axis. And that vertical distance between the two graphs from 1 to 8/3 is the distance between the function x and that constant function 1. The function x describes the upper bound on that length. The constant function 1 describes the lower bound. Now at 8/3, that does what change? The upper bound changes on those lengths. The upper bound is now described by that functional relationship y equals 4 minus 1/2 x in the context of x being independent. And all these infinite lengths happen from 8/3 now down to the value of 6, so we integrate from 8/3 to 6. The difference between these two lines in space and the difference between these two lines in space would be 4 minus 1/2 x minus that constant function 1. Right? This would be our approach in the context of x being the independent variable in that classical context where we think about this region of space formed by adding up all these infinite lengths that happen vertically between these two graphs in that region. Notice that did have to be approached piecewise. This would be approached using two separate definite integral calculations that would be added together to describe that one physical area of space. It would be this area added to this area makes the area of the region of interest in total. All right? In this orientation, we can change that orientation though. What if we were to consider this region of space not forming with vertical lengths, but forming over horizontal lengths? All right? Lengths that went from the left to the right in this region, starting on this leftmost bound and continuing over here to this rightmost bound. From here to here, from here to here, from here to here, from here to here, right? This region can also be considered to form over an infinite number of lengths starting here at a y value of 1 and continuing all the way up to this point in space at this particular value of y that you could find algebraically using a similar method to what we used to find 8/3 down below. Coincidentally, that value is also 8/3 along the y-axis. Now that's just coincidental there, folks. All right? So from 1 to 8/3, this region will form with a horizontal orientation of our region, where the infinite number of infinitely small lines will form horizontally in space and stack up on top of each other, starting here at y equal to 1 and continuing all the way up to this point at 8/3. And notice as they stack from 1 to 8/3, their lower, or I should say here, their leftmost bound, what defines where the lines start on the left, is consistent over those y values. And where those horizontal lines end at on the right are consistent over these horizontal values, or over these values of y from 1 to 8/3. So over the values from 1 to 8/3, right, there is no changing of roles in the values of what might define the leftmost or the rightmost bound. And this leftmost bound, this is going to be known as g of x, right? That is indicating smaller values. Sorry, that's going to be g of y. That's indicating our smaller values of that function g of y. What does it mean to be smaller in this orientation? It means to fall further to the left in our illustration, right? This graph over this region, this little portion of this graph falls to the left of this portion of this graph, right? This portion of this graph falls further to the right, which means it's bigger over these values of y from 1 to 8/3. So this relationship would be defining f of y, and this relationship is going to be the one we use to define g of y. This is y minus x equals 0. In the context here, x is going to have to depend upon y. X dependent, y independent, so we would have to solve for x. Solving for x, we would find x equals y here. So y would be the equation for g of y. G of y would equal just simply y. As for our rightmost bound, as a function of y being independent, x dependent upon y, we would have to solve this relationship for the value of x. And that's done just by subtracting 2y from both sides. X would equal 8 minus 2y. So 8 minus 2y would define this rightmost bound on these lengths. That would define f of y in this calculation. And we do see that in our setup. Within the context as y being dependent value in this description of space, we would be integrating from 1 to 8/3. Starting here at 1 on the y-axis, we would integrate all the way up to 8/3, which is 2 2/3, right? Which is right about here, along our y-axis. That entire region's forms, where our lengths form horizontally, starting closer to the y-axis here at, what is that, 8 minus 2y, or sorry, at y, and extending out to this linear relationship, which written as a function of y would be 8 minus 2y. So we're going to take this location minus this, and it will tell me this length at this particular value of y. I'm going to take this location minus this along my x-axis, right? It's going to tell me this length that's occurring at this value of y. And we're going to do that at all the infinite values of y from 1 to 8/3 and add up all those infinite lengths. That's the integration process. That's the essence of integration. And that should give me the total area over this region. Now, simplifying this integrand, I just minus 2y minus y is minus 3y. So my integrand is really just the linear equation 8 minus 3y. Its antiderivative is 8y minus 3 halves y squared, where evaluated from 1 to 8/3. Plug in 8/3 and subtract that result from what you get when you evaluate it at 1. Plug in 1, right? And you will get 25/6 units squared in value. What is that? 4 1/6 of a unit squared. Right? That will be the size of that region, the area of that region. That would be the same value the classical calculation will give you. If you go through this definite integral calculation and you go through that definite integral calculation and you add up those two results, you should also get 25/6 in value. But you will notice that classical calculation would be a little bit more tedious. in its calculation. You would have to actually calculate if you could just break it down to workload and making an integration 1 unit of workload, this would have 2 units of workload compared to just 1 unit. There would be twice as much workload in that classical calculation, right? You could get through this in half the workload that you would have that when compared to the classical interpretation. And notice, folks, problems are not going to present themselves in one orientation or another in a lot of cases. You're going to have to be the one that makes the decision as to how you might orientate yourself. So when looking at a net area question, where you begin is with what orientation do I want to tackle this with? And to do that, you ask yourselves, all right, I could have my lengths form vertical in space and scan across that region with your lengths forming vertical and see how they behave. Does the top or the bottom of those lengths, right? In this case, the top would change its description as we move from left to right over these values of x. So that caused these 2 separate integral calculations. You may actually see that also occur in the more contemporary orientation where y is independent, right? What we notice in this case, if we then scanned it, letting our lengths stack on top of each other, going from left to right to define that region, what defines the leftmost bound on those lengths and what defines the rightmost bound on those lengths does not change. So that makes for an easier calculation. And if we're looking to ease our workload, we certainly might consider this easier, or this calculation that requires less workload. All right. Now I say that, folks, that way, but the other aspect of this that also you have to keep in mind is once you decide on an orientation, you have to make sure that the integrand that you can form with the difference in that calculation of that orientation, you want to make sure that this integrand that you can form is integrable, that you can integrate it, right? A lot of the cases you'll see, right, it's going to be integrable in one form or another, right, in one orientation or another, but it's not guaranteed to be integrable in both always. So sometimes you may set it up in one orientation but present yourself with what is currently going to be an impossible integration for you. Whereas if you consider the alternative orientation, although it might be a bit more complex, it might at the moment be doable, right? It might be a doable integration. It might be integrable with the skills that you have. So you also have to keep that in mind as you're approaching these problems, folks. And it's practice. It's always practice, practice, practice. So make sure you're practicing out there. You're looking at some good odd problems to practice. Certainly the blackboard is a good place to practice. I've given you some practice in class. And, this is just more application of integration, folks. This is built on that fundamental idea of integration. All right? And that idea of integration, that fundamental idea of integration, it's what we used back in our previous lectures looking at displacement and distance traveled. And it's going to be, and future value and net change. And it's going to be used in some following lectures here where we're going to start to look at some more geometrical concepts in this integration process. It has an essence to it that we want to make sure that we also start to pick up on. And that essence started to come out in this lecture where when we're looking at the integration process, specifically the definite integral process, is we are performing an infinitely long summation. We are adding up an infinite number of values in our integrand's value, right? Right? We're calculating here an infinite number of horizontal lengths back here in this example. Right? There's an infinite number of horizontal lengths being calculated here and added up to make up this area of that region. That isn't the essence of integration. How that infinite summation is approached, though, is with the limit of a Riemann summation, right, in our calculation. And that goes back to the end of Chapter 5, folks, where some skills you should be bringing into this class. I will return to those ideas in a future video. I do want to kind of give you a video that would cover the proofs of these formulas, but let's get a few more formulas under our belt before we start to look at that. All right? So I'll be back with another video over all this material, and what do I keep doing that? Let me close that out and say I hope to see you then. I hope you're hanging in there, and I'll see you soon.